Jnanam paramam dheyam. Knowledge is supreme.
Friends, let us summarize what we have learnt in the last lecture. So, in the last lecture, we initiated discussion on the fluid, solid, non-catalytic heterogeneous reactions, and we looked at what are the different modes based on the nature of the non-catalytic heterogeneous reaction. That is, if the size of the particle which is actually involved in the reaction, size of the solid which is involved in the reaction, if that changes, if the size changes, or if the particle actually the size of the particle remains constant throughout the reaction. So, based on that, the mode of heterogeneous reaction can be different, and the resistances that are actually involved are different. And we also described initiated two different types of models. One is the progressive model, progressive conversion model, the other one is the shrinking core model. And then we looked at, because most of the reactions follow the shrinking core model, we initiated writing balances to capture the size of the particle as a function of time for the shrinking core model. So, let us, and also we discussed on different processes which may be rate controlling, and then let us continue from there. So, suppose if diffusion through the gas film controls the overall conversion, suppose diffusion through the gas film controls the overall conversion, then if the reaction is, let us say A, species A, which is in the fluid stream, reacts with solid B, which is in the particle core, and that leads to formation of certain products. And if we assume that if the diffusion through the gas film is controlling, which means that the concentration gradient is essentially in the gas film, and as all the other processes, that is diffusion through the ash layer, which is basically consists of the inert material and the product that may actually stick firmly to that layer, and the unreacted core which is present inside the ash layer. So, the diffusion through that ash layer is faster than the diffusion of the reactant species through the gas film, and also if the reaction that occurs at the interface of the ash layer and the unreacted core, if that is also very fast, then it means that the concentration in ash layer and in unreacted core of species A is approximately 0. So, which means that in the time scales where the diffusion of the species occurs, the concentration in the ash layer and the unreacted core of the species is approximately 0. Now, so we wrote a model in the last lecture, and the model is that captures the rate of change of the radius of the particle because of the heterogeneous reaction. Heterogeneous fluid solid reaction is given by r square dr by dt minus equal to minus kg, which is the mass transport coefficient, into the external surface area multiplied by the concentration of the species in the gas phase divided by 4 pi into the density of the catalyst, density of the solid which is participating in the heterogeneous reaction, not catalyst. So, now the external, we have assumed that it is a spherical particle. So, therefore, S external is equal to 4 pi into r naught square, where r naught is the initial radius of the particle and the size does not change, except that the unreacted core starts shrinking due to the occurrence of the heterogeneous reaction. So substituting this expression, we find that r square dr by dt, that is equal to minus kg Cag into r naught square divided by rho b. So that is the model equation, and now if we integrate this expression, then we will be able to find out what is how the radius changes with respect to time. So now we can integrate this expression between r naught and r. Remember that r is suppose if this is the particle and the unreacted core is actually present somewhere in the center, and the r naught is the initial radius of this particle and r is the radius of the unreacted core, which is a function of time. So, we can integrate this expression between r naught and r, which will tell us what is the speed at which, or what is the radius as a function of time. So, r square dr, that is equal to time dt. So, now integrating this expression, we can find that the relationship between the instantaneous radius of the unreacted core as a function of other properties and time is given by 1 by 3 r cube minus r naught cube, that is equal to minus kg r naught square, which is the square of the radius of the initial particle, initial core, which contains the solids which is available for the reaction to occur, and that multiplied by Cag into time. So, that is the expression for the radius as a function of time. Now, so we can rearrange this expression and we can find that time taken for reaching a certain core radius is given by divided by r by r naught the whole cube. Now, from this expression we can find out what is the time that is required for complete conversion. Now, complete conversion is achieved when all of the solid core has actually been consumed for reaction to form the necessary products. So, for complete conversion, r is equal to 0, that is the radius of the unreacted core has to be 0, which means that all of the solid which is available as reactant is now consumed. So, suppose if tau is the time taken for complete conversion. So, from this expression setting r equal to 0, we can find out that tau is equal to rho b r naught divided by 3 into kg into Cag. So, that is the time required for complete conversion of the solid which is present in the unreacted in the core to form the products. So, now by using the expression for complete conversion, we can now find out the ratio of the time taken to reach a particular radius divided by the time taken for the complete conversion. So, that is given by 1 minus r by r naught cube, and that is essentially obtained by taking a ratio of this expression and this expression. So, if we take a ratio of these two expressions, we will find what is the fractional time taken in order to reach a particular radius r. So, now if we define that the fraction unreact, what is the fraction of the core which is unreacted, then that is given by 1 minus x b, if x b is the conversion of the solid, b represents the species present in the solid, and that is equal to the volume of unreacted core divided by the total volume of the particle. So, that is given by 4 by 3 pi r cube, where r is the instantaneous radius of the unreacted core divided by 4 by 3 into pi r naught cube, where r naught is the radius of the initial particle. So, that is given by r divided by r naught the whole cube. So, therefore, from this relationship between the conversion and the instantaneous radius of the unreacted core, we can rewrite the fractional time taken to reach a particular radius as T by tau is equal to the actual conversion, and that is equal to 1 minus r by r naught the whole cube. So, the fractional time taken to reach a certain radius is directly equal to the conversion if the overall conversion is actually controlled by the diffusion through the gas film. So, next if we look at the diffusion through the ash layer, suppose if we look at diffusion through ash layer, suppose if we assume that the diffusion through the ash layer, that is the layer which is present between the unreacted core and the gas film. So, the species from bulk it comes to the surface of the core through the gas film, and then it diffuses through the ash layer in order for it to reach the unreacted core for the where the reaction occurs. So, suppose if the diffusion through the ash layer is actually the rate controlling step, that is it is the slowest step, and the other two, that is the reaction step and the diffusion through the gas film, if these two are actually very fast steps compared to the diffusion through the ash layer, then we can now model this system assuming that the diffusion through the ash layer is the one which controls the actual process. So, in this case, suppose if we assume that the reaction is species A in fluid form plus species B in solid form leads to the formation of products.
It must be noted here that the stoichiometric coefficient of B can take values other than 1.
And we can now suppose if r naught is the initial, suppose r naught is the initial radius of the spherical particle which is actually participating in the heterogeneous reaction, and suppose if there is an unreacted core and the instantaneous radius of this unreacted core, let us say if this is given by r of t. So, that is a function of time, and there is a gas film which is actually present around this particle. So, the gas film is present around this particle. So, the species A diffuses from gas film from the bulk to the gas film to the surface of the particle, and then diffuses through the ash layer. So, this is the ash layer and diffuses through the ash layer. So, therefore, we expect that if diffusion through the ash layer is the controlling step, then the concentration gradient of the species A is essentially going to be only in the ash layer. In all other layers, the concentration is going to be uniform. So, therefore, we can quickly sketch what is going to be we can intuit what is going to be the concentration profile. So, suppose if this is r naught, that is the radius of particle, and this is the center of the sphere, and this is r naught. And if this is r, that is the instantaneous radius of the unreacted core, then we can expect that if suppose this is that is the concentration of species in the gas phase, that is the bulk concentration, then we can expect that the concentration profile will essentially look like this, where in the bulk gas phase and in the gas film, the concentration essentially remains as the concentration as that of the bulk concentration, which is CAG or Ca naught, and there will be a gradient of the species A in the ash layer, and as soon as the species reaches the surface of the unreacted core, the reaction is very fast, and therefore, the reaction will immediately occur, and so the concentration of species in the unreacted core is going to be 0. Now, we can write a simple mole balance in order to capture the rate of change of the concentration of the species as a function of time, as a function of other properties of this system, and this will help in estimating how the radius changes with respect, radius of the unreacted core changes with time. So, let us write a simple mole balance. Suppose if this is the initial particle. Suppose if this is the particle at any time t, and the radius of the particle is r naught. Remember that the size of this particle is not changing, and if the unreacted core is present here, so that is the unreacted core whose radius is now r t, that is a function of time. And suppose if we take a small element, suppose if we take a small element and the thickness of this element is delta r, and if we assume that the positive r is the radius going outward from the center is the positive direction, then we can write a mole balance where we can say that the rate at which the species is entering this element minus the rate at which the species leaves plus whatever is being generated, that should be equal to 0, that should be equal to accumulation, sorry. So, now if we assume that the concentration profile in the ash layer, so this is the ash layer here. So, if you assume that the concentration profile in ash layer at any time is equal to the steady state profile which means that if we assume a pseudo steady state or quasi steady state approximation for the quasi steady state approximation for the concentration of species in the ash layer, then the accumulation is equal to 0. So, if we assume quasi steady state, this means that there is no accumulation. So, accumulation is equal to 0. So, therefore, we can now write a mole balance where the rate at which the species enters, if W A r is the molar flux at which the species is entering that element delta r thickness at r. So, that W A r at r is the molar flux with which the species is entering that element multiplied by 4 pi r square. Multiplied by 4 pi r square, it is a molar flux, but the balance is written in molar rates. So, W A r, which is the molar flux multiplied by the corresponding area at r, and W A r into 4 pi r square at r plus d r. That is the molar rate at which the species enters this element, and this is the molar rate at which the species leaves, plus nothing is being generated because the reaction is actually occurring at the unreacted core surface. So, therefore, generation is 0, and we have assumed that it is a quasi steady state approximation. So, therefore, the rate of change, therefore, the accumulation term is also equal to 0. So, now we can set limit delta r goes to 0. So, then we will get the model equation will reduce to d by dr W A r into r square equal to 0. So, that is the mole balance. That's the mole balance. Now, we need to know what is this W A r. W A r is the molar rate, and the process with which the species is actually entering that element is the diffusion. So, the molar flux can actually be related to the concentration using the Fick's law, and so suppose if we assume that it is equimolar counter diffusion. So, because there are two species which is participating in the reaction, species A which is in the fluid phase and species B which is in solid phase. So, suppose if we assume that if it is equimolar counter diffusion, if you assume equimolar counter diffusion, from stoichiometry we can actually discern that the flux with which the species A is actually entering should be equal to the flux with which the species B is actually reacting to form a certain product. So, therefore, WAR is given by minus DE, which is the effective diffusivity of the species, multiplied by DCA by DR. And so, plugging the molar flux. So, this is the molar flux, assuming that it is equimolar counter diffusion, that is the molar flux, and DE is the corresponding diffusivity. And plugging this into the mole balance, we find that the mole balance is d by dr minus r square equal to 0. So, now we need to solve this equation in order to find concentration as a function of position. So, remember that we said we will assume quasi steady state for the concentration profile in the ash layer, that is the instantaneous concentration can be assumed to be that of the steady state profile in the ash layer. So, the corresponding boundary conditions are at r equal to r naught, which is the outer rim of the particle. Remember that the particle size does not change. So, at r equal to r naught, we expect that the concentration of the species is equal to that of the bulk concentration or the gas phase bulk concentration. And at r equal to r of t, which is now, remember that the radius is now changing with time because the unreacted core is now shrinking. So, Ca equal to 0, because this is a diffusion layer, ash layer diffusion controlled process, and because, and also at r equal to t, there are fresh solid is present, the unreacted core, the reactant actually experiences unreacted core, which is now ready for reaction. So, on integrating, we can find that the concentration is given by Ca by Ca naught, that is equal to 1 by r, which is a function of time, minus 1 by r divided by 1 by r minus 1 by r naught. So, 1 by r is any position between r naught and r of t is the location of the unreacted core, and r naught is the outer rim of the particle. So, now if we sketch the concentration profile. So, if this is the center of the sphere and this is r naught, so that is the thickness of the sphere. So, this is decreasing r, and let us say this is r of t, the unreacted core is actually present between 0 and r of t. And so, if we plot Ca by Ca naught, then the concentration profile essentially it looks like this. So, it decreases from 1 all the way to 0 at r of t, because the reaction actually occurs quickly at this location. Now, in order to obtain in order to find out what is the radius of the unreacted core, we need to find out what is the expression for r of t as a function of other properties of the system. So, now we can because it is diffusion control, the molar flux at the interface at fluid solid interface, where the reaction actually occurs, because we have assumed that it is diffusion controlled in the ash layer. So, as soon as the fluid species reaches the surface of the unreacted core, the reaction is going to occur immediately. So, therefore, the molar flux at the fluid solid interface should be equal to the rate at which the reaction actually occurs. So, let us look at the molar flux at the fluid solid interface. So, molar flux will be WAR, which is equal to the diffusivity d multiplied by dCA by dr at r equal to r, and that is given by minus dE Ca naught divided by r square into 1 by r minus 1 by r naught. Now, because the reaction occurs immediately, the rate at which the molar flux at which the species actually reaches the unreacted core should be equal to the multiplied by the area should be equal to the amount of reaction that occurs. So, therefore, we can now write a balance on the elemental solid. We can write a balance on elemental solid in order to relate the rate of reaction and the flux. So, the rate at which the solid that actually enters in the ash layer, which is equal to 0, minus the rate at which the solid leaves the ash layer, that is equal to 0, and the rate at which it is being generated is basically the RB is the reaction rate multiplied by the area of the unreacted core, because the reaction actually is occurring on the surface of the unreacted core and the solids are not moving. So, therefore, the rate in and the rate out are 0, and this is the generation term, and that should be equal to the accumulation rate, and the accumulation rate is essentially given by d by dt of phi b rho b into the volume of the particle. Now, phi b is nothing but the volume fraction of the unreacted core, which is occupied by the solid. So, now plugging in the expression for the volume of the unreacted core, we can rewrite the balance as R b 4 pi r square, that is equal to d by dt pi r cube. On simplifying this expression, we will find that dr by dt, which is the rate at which the unreacted core radius changes with time, and that is equal to divided by phi b into rho b. So, now because it's diffusion controlled in the ash layer, soon after the species reaches the surface of the solid unreacted core, the reaction is going to occur immediately. So, therefore, the rate of reaction should be equal to the molar flux, the flux of reaction should be equal to the flux at which the reactant is actually reaching the surface of the unreacted core. So, therefore, R b that should be equal to minus WAR at R equal to R. So, remember that the minus sign here is essentially refers to the fact that the fluid, because the diffusion of species, the fluid diffusion of species A is in the negative direction. So, we said that the sign convention is we assume that the outward direction is positive and the diffusion of the species A is actually going from outside to the inside of the particle. So, therefore, the diffusion is actually in the negative r direction, and that is why there is a minus sign that has been inserted here, and that should be equal to dE C A naught divided by r square into 1 by r minus 1 by r naught. So, this expression relates the rate at which the solid is being consumed for reaction and the other properties of that system. So, from here we can find out we can rewrite the expression for dr by dt, which is the rate at which the radius changes with time, that is equal to divided by 1 by r minus r square by r naught. So, now we can integrate this expression at time t equal to 0, that is when the reaction has not started, then the size of the unreacted core is equal to r naught. And so, we can integrate this expression and we can find out that the time taken to reach a certain radius of the unreacted core is given by rho b r naught square into phi b, which is the volume fraction of the unreacted core which is occupied by the solid, divided by 6 into diffusivity into C A naught multiplied by 1 minus 3 r by r naught square plus 2 into r by r naught cube. So, that is the expression for, that is the relationship between the time that is taken to reach a certain radius and the other properties of the system.